moving on to question 4 now, we have a very long question here, and it's split up into a few different parts, but the main core of this question is looking at the chi-squared test. So, let's just have a look at what we've got going on. So we've got this distribution here of oak trees in some woodland, and they're dividing the woodland into 80 equal squares and recording the number of oak trees in each square. So the results are summarised here in table 1, and for part A, it's asking what model should Liam use to describe the number of oak trees per square. Well, the key for this part of the question is to use this bit of information here, where it says Liam believes that the oak trees were deliberately planted with 6 oak trees per square, and that a constant proportion P, so this is the important bit, the constant proportion P survived. So, what this is saying now is that it wants us to write down how this is distributed. So, question 4a, what is the distribution here? Well, if I put T for the trees, well, the key here is where it says constant proportion. Remember, when we're looking at distributions, if you ever see the fact that it's in proportion, it's a good chance, or it's more than likely always going to be binomial. Okay, so we know this is going to be a binomial distribution. Okay, so T is distributed binomially. My N, well, how many oak trees? 6 oak trees per square. That's my fixed trial here, my fixed number, so that must be my N. And my P, well, we don't know what P is, so we're just going to write P like that, right? We don't know what P is. We can later work this out, but for now we don't know what it is, so we'll just put P. Okay, and that's simply all you've got to do for the first 2 marks. It's just understanding that it needs a binomial because we're talking about proportion. Okay, so that's part A done. Part B is 7 marks, quite a bit of work to this one, so let's have a go at it. So my mouse has decided to stop working. Okay, let's have a look at it. So part B. So this is kind of a bit of an unusual format because there's literally no room for me to write down here. I'm doing it down the sides today for this one, so hopefully you can follow along. I put it in yellow just so it makes it a bit easier to see. So let's have a go at part B. So we're given some expected frequencies in this table here, table 2, and part B just asks us to complete the test here for a chi-squared test. So let's have a look at what we've got to do first for this. Well, because it's a test, let's write down a H0 and a H1. So H0, well, my H0 here is we're testing whether this model is going to be suitable. Okay, so if we're testing whether the model is suitable, H0 will mean that it is a suitable model, so T distributed binomially with those parameters is suitable. Okay, and a H1 will just simply be T distributed binomially, again with the same parameters, is not suitable. Okay, so that is not suitable. There we go, so just about enough room. So we've got our hypotheses. Now let's have a go at actually doing this question. Now the first thing is, we're not given a P. Now we can work out this P, and because we'd have to work it out anyway, it changes our degrees of freedom. So we're not going to need the degrees of freedom till the very end of the question, but let's just work out the P anyway. So P, well, how do we work out P? Well, P will be my probabilities of success. So my success would be kind of like your discrete random variables. If you've got no oak trees here, you times it 1, we've got no oak trees. If there's 1 oak tree per square, we've got 4 of them, we've got 4. So we're going to have to sum all these multiplied together. So for example, I'll start rounding down and then I'll just give the answer. So it'd be 1 times 4 plus 2 times 21 plus 3 times 23 plus so on and so on. So that will be my numerator. And my denominator, now Liam thinks that there's 6 oak trees per square and that it's 80 equal squares. So that, my denominator will just be 6 times 80, which will be 480. So my denominator is much easier. That's going to be 6 times 80. Okay, so P. This here, my numerator, this sums to 264. And my denominator is 480. And if you calculate this, you get 0.55. Okay, and because we've had to work out the probability for this question, sometimes you'll be given it, but for this one we wasn't. So my degrees of freedom we can work out after. But the formula for this will now be V equals N, well that's my number of columns for my expected frequencies, minus 2. Okay, so we will need that for after on. We'll just write that down now. So now let's jump into working out the formula that we need. So the formula you can use is my observed minus my expected all squared divided by my expected. Okay, and we need to do this for our values here for my expected and my observed. The first thing we always have to check though for the expected, do we have any expected values less than 5? Okay, so this one's just above. Looking across, then there's just this one. So your expected frequencies that are going to be below 5 are usually either at this end of your table, or they'll be at both ends. Now in this case, it's just this end here, it's just this one here that's problematic. So we have to pool these two together now. You always pool it with the adjacent column. So if you pool these together now, add these together, and what you get is 13.08. Okay, so if I just write that up here, just so you can see it a bit better, 13.08. So in essence now we've got 1, 2, 3, 4, 5 columns here. So we can actually work out the degrees of freedom straight away. So that'll be V equals 5 minus 2. Okay, so we've got 3 degrees of freedom. So we've got 3 degrees of freedom. I'll just put DOF. So we've got 3 degrees of freedom. Now we just need to work out this formula here, and then we need to sum it up to work out our chi-squared value. So to do this now, well, because this first one here is 0 or 1, you're going to have to add your frequencies here. So that would be 5 minus 5.53. So I'll just start doing the first one. So it'll be 5 minus 5.53. Square that. Then divide it by your expected, which was 5.53. So you've got to sum all of these up. Plus, and then you do it again. So it'd be 21 minus 14.89. 14.89. That's all squared. And then you divide that by 14.89 again. Okay, and you're going to have to keep doing that all the way up to the very last one. So that'll be your 5th column here. So we close that. So I'll write them down individually. So what I got if I do them up here. So my first one, so that'll be this one. That was 0.051. My next one was 2.51. Next one, 0.0654. Just go underneath for the next two. I also got 3.84, so you should get 5 in total. And then finally, 24.771. Okay, so them are my 5 values. There is another formula you can use. You can also use, if I just do it down here, you can also use the observed squared, so observed squared over the expected. You can use the sum of that minus your n. Both these methods will work. Okay, so whichever method you're more comfortable with. This one, okay, this formula is in your formula book. This one isn't. This one I think is a little bit easier sometimes, but this one is in your formula book, so you don't have to actually memorize it. It's just whichever you prefer working with. Okay, so these are my 5 values. So all I've got to do now is sum them, and I've got my value. Okay, so if you sum all these, your expected frequencies here. So I've accidentally copied one down wrong. I've accidentally copied this one down wrong. I'm going to say that's incorrect. This one here. So I'll just scribble that out. That one there should be 1.85. I'm going to say that one's much larger than the others. 1.85. Okay, 1.85. So we've got all them now. All we need to do is add them together. So if you add these together, so the sum of all these, well, that's going to be equal to 8.313. Okay, so 8.313. So now we've got the degrees of freedom. So this is my test statistic. So test statistic 8.313. My critical value. So now you need to use the formula book. So it's page 36. What significance level? 5% significance level. So make sure you read from 0.05, not 0.95. That's a common mistake. So 0.05, and we've got 3 degrees of freedom. So that'll just give you a critical value of 7.815. Okay, so 7.815. So because our test statistic, I always struggle saying that word, is bigger than my critical value, we need to reject H0. Okay, so reject H0. Reject H0. So what did we say? So this distribution is not suitable. So reject H0. T distributed binomially is not suitable. And there we have it. So we've shown that this is not suitable. So we've got a bigger test statistic than my critical value, so we reject here. Now, if that had been smaller, we would have accepted, and this would have been suitable. But in this case, it works out that it's not suitable. Okay, so again, you can use this formula down here. This will give you the exact same value for here. Okay, whichever method you've been shown more in class, or you've used more in your formula book, or anything like that, whichever you're more confident with, just stick with that. Okay, but that is part B complete. So that's 7 marks there. So now, let's have a look at part C. So part C, we have to find the value of S and T. So this person here believes that a Poisson distribution could be used to model the number of oak trees per square. And she calculates the expected frequencies given in this table here. Okay, so these are my expected frequencies again. We have to work out S here and then T here. So how would we do this? Well, let's just write it in the probability now, because this is a Poisson. Let's work out the probability of a Poisson distribution. So P. So my formula is e to the minus lambda times lambda to the x divided by x factorial. Okay. So that's my formula for working out the probability. Well, if we say the probability that x equals 2 is equal to this formula, and we just submit x equals 2 here, and then we do the same for x equals 4, for example, we can obtain a value, right? And we've got it in terms of x is equal to 2. We can't use this one here because it's 0 or 1. We don't know exactly what x would be, and we don't know what it would be here. It's 6 or more. So the best one to use are the ones that we have an exact value. It's 2 and it's 4. Using these, we can use x. We can put it both in terms of probability of x equals 2, probability that x equals 4, and then we can use this to obtain a value for lambda here. That would be our mean. And once we've got that, we can then work out probability that x equals 3, and probability that x equals 5. Now let's just be clear, when I work this out, these aren't the exact probabilities, because don't forget these here, these have been multiplied by 80 to give the expected. So if you divide these by 80, then that would actually give you your actual probability, okay? So that's why they're bigger than 1, because clearly you can't have a probability bigger than 1. So just to make that clear, because that's what will happen here now. When I work these out, they're going to be larger than 1. So just to be clear, obviously my probability isn't bigger than 1. But if we do that now, so the probability x equal to 2, that's going to be e to the minus lambda times lambda squared all over 2 factorial, which is 2. Okay, so that's that one nice and easy. X equals 4. Again, e to the minus lambda to the 4 all over 4 factorial. So 4 times 3 is 12, times it by 2, then times that by 1. I'm just going to get 24. Okay, so now we've got these two probabilities here. Now, I need to work out a value for these. Well, we know this is equal to 16.07. Okay, using the data we've got here, that's 16.07. This one's equal to 14.58. So we can use this now to work out our probabilities for 3 and 5 once we've got a value for lambda. So what I'm going to do now is I'm going to divide both of these. Okay, so it doesn't matter which way you divide. You can either do 16.07 divided by this, or you can do this divided by this. Either way, it doesn't matter. As long as your workings are all, exactly fine, then you'll get the same lambda value as I will do it. So I'm going to divide it as 16.07 over 14.58. But like I said, this does not matter at all. Just be very careful in your working. So now 16.07 is this, so it's e to minus lambda squared all over 2 times. So if you're dividing, I'm going to times it by 1 over this, so it's going to be 24 over e to minus lambda to the 4. Okay, so that's my working there. Now we just need to actually evaluate this. Well, 24 over 2, so that'll cancel with that, and that'll give me 12 there. My e to the minus lambda will cancel with that one there. So all I'm going to get is 12 lambda squared over lambda to the 4. 12 lambda squared over lambda to the 4. Okay, and this is equal now, if you actually evaluate this, I'm going to write it out in full, so it's going to be 1.102194 787. Okay, 787. So that's equal to this. So now this, we can simplify this again here. That's going to be 12 over lambda squared. So therefore this is equal to 12 over lambda squared. So now I'm going to times this across by lambda squared. So if I do it up here, I'm going to get 1.102 787 lambda is equal to 12. So now you've just got to divide 12 by this, and then we need to square root it because this is lambda squared, so we're going to say we're missing some at lambda squared, and then square root your answer. Okay, so if you do that, what you'll obtain is that lambda is equal to 3.299601153. Okay, so obviously you could round that, but for now I'm just going to keep it as 4 degrees of accuracy because we can use this now to obtain these two probabilities here. So for now you can either use the formula again here, or you can just plug this bit in on your calculator now. So I'm just going to put this on my calculator just to save time, and I'd recommend if you've got a graphical calculator, guys, always utilise it for these questions and for your further stats exams in general. Really important skill. So looking at the probability that x equals 3 now, plugging this in on my calculator with this mean and my x being equal to 3, what I'm going to obtain is that this probability is equal to 0.22. Again, I'm just going to write these out in full. 0.22091973, and my probability that x equals 5. That will be equal to 0.1202 6172. Okay, so we've got our two probabilities. Now we just need to times these by 80, right? So that'll give me my S. So therefore, S is equal to probability of x equals 3 times 80. So I'm not going to write all this out again. I'm just going to do the calculation and then round it to 2 decimal places. So that'll give me 17.67, and then T, same again, it'll be a probability but with x equals 5. Times that by 80, and that's my value, just round it to 2 decimal places. And if you do that, you'll get 9.62. Okay, so there we go, we've got the answers, or the values for S and T, with both to 2 decimal places. So let's clear all that. So now we're on to part D. So this question just feels like it's going on forever. It's quite a long one. I might leave the timestamps in the description just so you can skip through if there's a certain part you want to get to. So let's carry on. So part D. So a similar question here. We have to write down the hypotheses to test the suitability of this model. So just like we did with part B here, I've got my two hypotheses. So H0. Well, we're testing whether the Poisson distribution is a good model or a good fit for the distribution. So if I just write that, Poisson. Remember H0, that is a good fit. So Poisson is a good fit, or a good fit for the distribution. And then H1, Poisson is not a good fit. Okay, so there we have it. So H0, that is a good fit. H1, it's not a good fit. So that's part D done, nice and easy, just 1 mark. Part E now, we're given another test statistic, 8.749. We just have to complete the test, okay? So let's look at our expected values first. So part E, well, we have S, that was, just give me a second, I've moved them out of the way. So my S was 17.67, so we'll just write that over here, S equals 17.67, and then my T, that was equal to 9.62. So S and T, that's these. Well, all these values are greater than 5, right? So we don't need to do any pooling. So that's the first thing. So no pooling needed. So the good thing is that we don't need to do any pooling. So now let's work out my degrees of freedom. So my degrees of freedom, how many columns have we got? 1, 2, 3, 4, 5, 6. It's going to be 6. And again, we're going to subtract 2. Because we've got for the totals, and we've got it because we estimated lambda, okay? So that'll be 4 for my degrees of freedom. Again, we're going to use page 36, right? So we're going to use page 36, because I just need a critical value now, to compare this test statistic to. So critical value, again, page 36, this will give you 9.49. And again, it's a 5% significance level, so it's 0.05, and then go across from 4. So you get this 9.49. So this time, my test statistic is smaller because it's 8.749. So because it's smaller, we have to accept here. So therefore, I accept H0. So that means the Poisson is a good fit. So Poisson is a good fit. For Simon's model. So there we go. So that's part E done. So nice and easy. You just got to work out the degrees of freedom, work out your critical value, and then just accept based on the fact that it's smaller. And then finally for part F, it says, using these results of the test, explain whether the origin of this woodland is likely to be cultivated or wild. Okay, so we've got to use all the previous information we've just worked out from part A, B, C, D, and E to give us the answers for F. So what it means, or what it's asking, is that are these trees basically planted randomly, so they're wild, or are they planted in a more specific manner, maybe to a pattern, so it'd be cultivated? Well, what we just worked out is that Poisson is a good fit. Poisson, good fit. Now, if Poisson's a good fit for this model and this distribution, what that would suggest is that they are planted more randomly, because binomial, in theory, gives us a more proportionate amount. It's going to be planted almost methodically. But with it being Poisson, what that implies is that it's almost planted randomly. Okay, so planted randomly. So planted randomly. So if they're planted randomly, that would suggest that the origin of the woodland is likely to be wild rather than cultivated. And there we have it. So that's question 4, finally fully complete.